Okay, so as I said, I'll make a screenshot or a PDF of this and put it in an email, and then also now I'm um, recording the meeting today. So when I post that, that should be should be there for everybody. Okay. Any no questions on this, I assume?
None from me.
Okay. Mike and Josh, you're good. So
Yep.
we had about 5 or 6 people on Monday afternoon. I just hope they don't hit me with everything all at once, because I'll just have to say no, I can't handle it all. So here's our prez for today. Let's take a look at this, because we're going to be talking about tolerancing today and shaft and hole assemblies, and a lot of good stuff. And this is where I start to wonder whether or not people are going to pick it up on their own. So let's take a look at it. You know, tolerancing, it's the amount of size variation that's permitted, and it's your decision as to the variation size, large or small. Here are 2 dimensions that are basically the same. These are limits. That's telling us that whatever this part is can be anywhere from 994 to 1.005 when we when we measure it. And so the limits are the 2 numbers of the low and the high end of the tolerance, I guess. And then the tolerance itself is the difference between the 2. So if we say a shaft can be a diameter of 994 to 1.005, those are the limits of the size of the shaft when you measure the overall size. Let's say it's diameter. The tolerance is the difference between the 2. So the tolerance is 11 thousandths of an inch. Interchangeability. When parts are mass produced, it's important that any part manufactured can replace any other part without affecting function. The parts are considered to be interchangeable. When we looked at that video of the Airbus plane being engineered and assembled back in the beginning of the semester, there were, I don't know how many million parts that went into that plane. And it's a cinch that, if they're producing hundreds of planes, that one manufacturer can't make all the parts, right? So they have to delegate the responsibility of all the part production to a number of different machining outfits all over the world. So everybody has to be able to read the same blueprints and produce the same parts, so that regardless of which manufacturer they came from or machinist, that the parts all are within the same specs for size, shape, and function, so that any one of them can be used from any one of the suppliers. That's interchangeability. So interchangeability first came about, at least in this country, back in the right around after the Civil War, because and it was basically introduced by munitions manufacturers or gun manufacturers. They had an issue in the Civil War with who are some of the carbine manufacturers. They were the single manufacturer was farming out part manufacture to to more than one supplier, and actually I'm not saying that correctly. Even if they were making their own parts, they were kind of making everything individually. So they would kind of fit parts. If they didn't fit together properly, they would kind of massage them, sand here, file there to make everything work. The problem became then in the field, if you had a gun, with or a rifle with a broken part, and you found another rifle, same manufacturer, same model, everything else, you couldn't necessarily use the parts from that rifle to, and have them work in yours because they were of different sizes. So they finally figured out that they needed to create, blueprints for these parts that had tolerances on them, so that regardless of where they were made or when they were made or who made them, that the parts would all be interchangeable. And that's pretty much when it came about. Like I said, at least in this country. I'm not sure about the rest of the world. So how does interchangeability affect tolerances? Well, the design specifies how much one part can vary compared to the next and still function properly. So when we look back on the numbers that we saw before, if I have a part that comes in at this diameter, a shaft, and the same shaft, same part number of the shaft comes in at this from somebody else, or the next one I pull out of the batch is this dimension or somewhere in between these two, they're still considered to be interchangeable. Even though there's that much variance, they'll still work within, the assembly of the rest of the parts. So tolerances are the way that you communicate to the machinist or the part manufacturer how much variation the design can tolerate. You hold tolerances too tight and the cost goes high, and too loose and the design might not function properly. So we'll see that when we start looking at fits between shafts and holes. Factors that influence the proper tolerance for a feature. Choosing the correct tolerance for a particular app depends on the design intent, the cost, how it's manufactured, and experience with some similar designs. So, if you know that that a trigger, fitting into the main frame of a gun. I hate to keep using these as examples, but because I started talking about rifling and the Civil War, I'm kind of stuck on that. But anyway, so if you know from experience, let's say you've seen other designs where there you can allow the slot that the trigger pivots in, to be, have a fairly loose tolerance and have it still function properly. Then you know that again that when you go to manufacturer B, that you can probably use some similar types of tolerances and still be okay. And again, the tighter you hold something, like we talked about, even with surface finish, anytime you increase the amount of work that has to be done on a part in order to produce it, the more expensive it becomes. So somewhere along the line, yeah, everybody okay?
Yeah.
Okay. One thing I haven't done is, and I guess we've all got microphones for this class, so I'm not going to worry about it. The afternoon class, I got one or two students that don't have mics, so I got to make sure the chat's open for them, so that they can pose a question if they want. So standards are needed to make it possible to manufacture parts at different times, different places that still assemble properly. And since we're working with, the ANSI standard, we have to kind of assume that that's what the standard does for us, rather than everybody having their own set of standards, which they still do. You know, you go to machine manufacturers and they all have variants of some standard, whether it's the ANSI or some company that the guy that owns, you know, the present company used to work for, and thought that their standards were pretty good. So he decides to use it, you know, those same standards, and sometimes, you know, they're mostly they're good, but sometimes they're dated, and you know, you need to take a look at it and see you know, what you can update. So standards are needed to establish dimensional limits that are, you know, for parts that are supposed to be interchangeable, and they also document collective history of what works for various applications. It's kind of like expanding on what the previous slide said. So I don't want to talk about this too much anymore. I want to get to the meat and potatoes of it, which is this right here. So first we're looking at different tolerance types, or how they're specified. This one is limits. We already talked about limits because we had to do a little bit of limiting and tolerancing in our one project, the P39, right? So we did tolerancing without even, you know, without really knowing what we were doing, I guess, unless we're obviously you know, already versed in it from working, but some of us aren't. But at least we got the formatting down a little bit, you know, whether we're limits or bilateral or symmetric. So limits are, this is what limits look like again. The upper limit is above or to the right of the lower limit, which I have some issue with when we're talking about holes and shafts, because when we're talking about material, this is a maximum material situation for a shaft, because when you're turning a shaft, you're starting with a piece that's oversized, you know, or whether, you know, and then you're slowly bringing the OD down to where you want it. So this is the number you're going to shoot for to begin with, and if you happen to miss it, then hopefully you still wind up within, you know, somewhere in between these two limits. If you're doing a hole and you're shooting for, you know, and the hole limits look like this, then if you shoot for this and you miss it, well, it's too late to get the, you know, you can't put back material back into the hole to get it smaller. So you're already done. You know, the part's already ready for the scrap heap. So I like to say, if you're writing limits for holes, write them this way, because now you're saying this is what we're shooting for, and if we don't make it, we can hopefully fall within this end of the tolerance, and wind up with a part that's still good. And I kind of prefer limits to anything else because you can do that. So then we have the plus minus tolerance, which is bilateral. In SolidWorks calls it bilateral. So you give the nominal, and then say it can be plus a certain amount or minus a certain amount. Undersized, plus a certain amount oversized, minus a certain amount undersized. And then for anything that isn't specific to the dimension, we go back to the tolerance block and the title block, and use those dimensions, those tolerances to control our part. So why do we study shaft hole? Well, it's a common assembly in manufacturing, and it's pretty good at illustrating some of the concepts and definitions that we talk about. The shaft and the hole can vary between a maximum and a minimum diameter, and that affects how well they'll fit together. So if we've got a shaft, you know, so when we think about it, when we look at our shaft and hole tolerances, if our smallest shaft is bigger than our biggest hole, the shaft's not going to fit, is it? Unless we force it in there.
Mhm.
So you have, you know, this is why the shaft hole assembly is not as a pretty good one to use to demonstrate the different concepts. By the same token, if the largest shaft diameter is way smaller than even the smallest hole diameter, then we're going to have a pretty loose fit, and that may not be what we want. So again, so let's look at this, and of course, this is an exercise in the book. It's you know, part of the chapter discussion, so it's not it's not a required assignment. But let's just take a look at the information that's here, the diameters and the limits of the hole, of the shaft, excuse me, and the limits of the hole, and try to fill this thing out. Let's just walk through this one and then see if we get the idea, because there's more than one example. So the limits for the shaft should be, I believe, 0.51 to 0.47, and the limits for the hole should be 0.49 to 0.50. So they write this is how they write the shaft, though. So the limits of the shaft are 0.47 to 0.51, which seems, I don't know. Again, we're looking at the smallest number, smallest diameter first, and the largest diameter second. And when you're actually making the part, you're going the reverse way. You know, you would hit the 5.1 before you'd hit the 4.7. So I'm not real comfortable with this, but this is the way the standard displays and portrays this stuff. So I'm just going to go with it. So for the hole, that looks good, right? 0.49 to 0.50, because when you're boring the hole, or you know, whatever you're doing to come up with this final size, you're certainly going to hit the 4.9 diameter before you hit the 0.50 diameter. It's the same thing with these dimensions. I think these dimensions, if you're going to show limits this way, that the hole limits should be shown the opposite way. Because when you look at this dimension, what's the first number you see? When I look at a dimension like this, the first number I see is the top number. And I know from experience there's more than one time that a machinist has seen that number and said, oh, that's the number I got to shoot for. And, you know, he does it for a hole, and he's got a little burr or something on his mill, his tool, and he oversizes the hole. And he says, you know, and then the hole is junk. Well, if he had been shooting for the 4.9, he might have still made the 5.0, you know, with a bad tool bit. So my opinion is that the hole limits, when you're showing them as limits, they should, the small number should be on top and the larger number should be on the bottom. And for shafts, the larger number should be on top and the smaller number should be on the bottom. And it all has to do with maximum material. What is the maximum material of the shaft?
51.
51.51, that's correct. So as the shaft gets smaller, or it starts to lose material, the diameter gets smaller, right? The maximum material of the hole is 0.49, right? Because we're talking about, the hole has no material. So we're talking about the material that surrounds the hole. So a smaller hole has maximum material around it. So if you go by the rule of thumb that a limit dimension should always show the maximum material on the top and the minimum material on the bottom, then what I'm saying would be correct. We would put the 4.9 on top and the 5.0 on the bottom for the hole, because that's maximum material. And that should be on top. Here, maximum material is already on top. But the standard doesn't do that, because, and I think it's because they feel like it might be too confusing to some people. If you've got shafts and holes in the same drawing, and you've got them dimensioned that particular way, I can tell you from experience that I've dimensioned it that way, where I've kept the maximum material on top, and no one's ever had an issue with it. As a matter of fact, I've had machinists tell me that they prefer it that way because, like I said, when you look at it at either one of these dimensions, the first number you see is the top number. So I prefer it that way. And I guess if I'm writing them out this way, I'd prefer the maximum material to be the first number. So the shaft limits, in my opinion, should be 0.51 to minus, to 0.47, not minus, but 0.51 to 0.47. But this is the standard. So that's what we go with in the class. So what's the basic size of these two two features? Pardon me?
Half inch.
Half inch, right? There's one basic size for both of them, and it's whatever the nominal is, for each one. Whatever the even numbered nominal would be. So when you look at, it's not just and it's not just the difference between, or the midpoint between these two, obviously, because neither one of them comes up to 0.50. But somewhere within this limit is 0.50, and obviously 0.50 exists within this limit because it's one of the numbers. So the basic size is 0.50, or half an inch. What's the tolerance on each one of them?
The shaft's got 4 thousandths and the hole's got 10 thousandths. Actually, 10 thousandths.
10 thousandths?
Mm-hmm.
And the shaft has how many thousandths?
40. Excuse me.
40 thousandths, right?
Yeah, 40 thousandths, right.
Yeah, 40 thousandths. So 0.04 is 40 thousandths, and 0.01 is 10 thousandths. Does everybody see that? I'm assuming you do.
Yeah.
Okay. It'd be. I wish there was a way you could give me a high sign or a yes or a no without having to necessarily unmute yourself and.
Sorry, I just have a cold. I just don't want to breathe into the mic.
Yeah, we don't want those COVID-19 virus viruses to come traveling through the wires. That's kind of like everybody hoarding water. It's like they honestly expect the water supply to get contaminated or what? Even if they're sheltered in place, that 99.9999% of everybody that's sheltered in place is running water. So,
well, if we all turned our cameras on, we could just give you a thumbs up.
Yeah, well, right, but I don't expect anybody to turn the camera on necessarily if they don't want to either. So, you're forced to have me look at you in class, but you don't have to. You don't have to subject yourself to scrutiny. In a situation like this. So, all right, maximum material, as I kind of talked about already, is the size of the part when it consists of the most material. In the case of the shaft, it's when the shaft is the largest. In the case of the hole, it's when the hole is the smallest. And least material condition is the opposite. When the shaft is smallest and the hole is largest. So let's look at this situation again. What's the maximum material condition of the shaft? 0.51. Yeah, 0.51. And the hole would be?
0.49.
0.49. Yep. And so least material condition is going to be the other end of the limit. So without forcing anybody to make a statement here, the least material condition of the shaft should be 0.47, and the least material condition of the hole should be the largest hole, the least amount of material around it, which is 0.50. Seems pretty straightforward, doesn't it? So what's the maximum clearance? What's the definition of that? Maximum clearance is the maximum amount of space that can exist between the hole and the shaft. So the max clearance is going to be the least material condition of the hole, which is the largest hole, and the least material condition of the shaft, which is the smallest shaft. So the maximum clearance is going to be the largest hole and the smallest shaft. The minimum clearance is going to be the opposite. The minimum clearance is the minimum amount of space that can exist between the two. And so the minimum clearance is going to be the minimum material condition of the hole, which is the, the maximum material condition of the hole, which is the smallest hole, and the maximum material condition of the shaft, which is the smallest shaft. The largest shaft, excuse me. It gets confused. See, it gets a little confusing when you do it this way. I mean, it's a lot easier when you're looking at the, at the parts and the dimensions that are on it. But the minimum clearance is again the maximum material condition of the hole, which is the smallest hole, and the maximum material condition of the shaft, which is the largest shaft. So smallest hole, largest shaft is minimum. Largest hole, smallest shaft is the maximum clearance. So looking at our two examples again, what's the maximum clearance between these two?
Which one?
So we're looking at the maximum clearance between the hole and the shaft. So that would be the smallest shaft and the largest hole, and it would be the difference between the two. So we're going to take the shaft and subtract, well, let's see how they do it. I don't want to say it. I don't want to say it that way if they show it a different way, but the maximum clearance is going to be the smallest shaft, 0.47, the largest hole, 0.50. So it should be 0.03.
Yeah.
Right? Right? Does that make sense?
Right.
Yeah. So then the other one should be 2. 0.02 then.
Because we're going to have the so the minimum clearance is going to be 0.02.
Yeah.
Okay. But it's not going to be a positive number.
Negative 0.02.
Yeah, because if you look at this information, you see the minimum clearance is the maximum material condition of the hole minus the shaft. Hole minus the shaft on both of them. So if you go back to this guy and you take the hole minus the shaft, it's 0.49 minus 0.51. So your minimum clearance is going to be minus 0.02. Can anybody tell me what kind of a fit that is?
Press fit?
Yeah, this is going to be what they call a press fit, because the hole is actually 20 thousandths smaller than the shaft. And that's going to be one heck of a press fit. Mm-hmm. trying to get these two together to get started is going to be pretty interesting, because it doesn't sound like much. It's only 10 thousandths on a side when you think about it, right? 20 thousandths overall on the diameters, 10 thousandths on a side. But try pressing that in without some massaging, like heating the heck out of this part and freezing this part, to get them to shrink and expand to the point where you can get a normal, like, press fits are 3 or 4 10 thousandths, 5 10 thousandths, some usually under, for the most part, under 1,000th of an inch interference. and now we're talking about 20 thousandths. But for the sake of demonstration, this is not realistic, but the numbers are good to demonstrate the differences. So that's just an aside. So that's what the negative clearance means, is that you've got a press fit. So here's some examples of clearance and interference fits. Clearance fit, right? Lock and key. If it was an interference fit, the key wouldn't go into the key slot, would it? Door in a door frame, the door wouldn't shut, and I'm sure we all have doors in our house that are interference fits at some point. And coin slot, that's got to be a clearance fit, right? The coin wouldn't drop into the slot and down the chute that it goes down and does whatever it does without some clearance. Interference fits, cap it for a pen. I like the second one, a swimsuit. You definitely want to have an interference fit between you and your swimsuit. Otherwise, you won't be wearing it for very long. And a battery, a AA battery, and the slot that it fits in. Yeah, I mean, it's interference, as a result of the spring, but that spring does create interference between the battery and the opposite contact and itself. So yeah, AA battery and a slot. So what are the different types of fits that we can have for shaft and hole assembly? Well, there's a whole myriad of them, but the basics are a clearance fit where there's always a space, regardless of what the minimum and maximum sizes for the hole in the shaft can be. There's always going to be some clearance or space. The minimum clearance is always greater than 0. Interference fit where there's never a space, regardless of minimum and maximum sizes. So that means the maximum clearance is always less than or equal to 0. So if it's equal to 0, it's called a line contact situation, but it's still, in my opinion, it's still interference. Because later on they talk about line contact as being either one, interference or clearance. And then there's transition, where there could be a space or there could be no space, which is kind of what we saw in our previous example, right? In one direction, we had clearance, and the other direction we had interference, right? When you look back at that, when our shaft was 0.49 and our hole was 0.50, we had clearance. But when the shaft was 0.51 and the hole was 0.49, we had interference. So that was a transition fit. And then they talk about line fits, where they're exactly the same size. The max clearance could either be greater than 0 or equal to 0, in which case there would be, according to them, a line fit would be, could still be an interference fit. Whereas up here they say, if it's equal to 0, yeah, I guess they say if it's equal to 0, it could still be interference. But if here they're saying if it's line-to-line contact, which means they're both the same size, you could have clearance. Well, the way I look at it is if you have clearance, if the shaft will go into the hole, even though they measure the same size, they're not really the same size. There's something going on. There's a few 10,000ths or 100,000ths or microns difference between that you can't measure that allows them to fit together. Because if they're truly line to line, it should be an interference fit. That's my opinion. So let's look at the basic size and the type of fit given the limits for the shaft and the hole in this exercise. Our shaft limits can be 1498 to 1500. The hole can be 1503 to 1505. What's our basic size?
1.500.
1.500. That's correct. And it's, yeah, I don't like the fact that this pops up, but it's clearance, right? Because no matter how big our shaft is,
Still going to go in a hole.
it's still going to go in the hole because the hole minimum size is 3 thousandths bigger than the largest shaft. So this is what you have to look at to find out what, you know, what type of fit you have. You look at the smallest hole in the largest shaft, and if the hole is bigger than the shaft, then it's clearance. You know these are going to be clearance because this is the largest hole in the smallest shaft. If the opposite is still clearance, then you know that these are going to be clearance too. So I kind of look at these first, the largest shaft and the smallest hole, to find out what I got. And then I go and look at the other two. So what's the basic size of this one right here?
0.750.
Yeah, 3/4 of an inch. And what kind of a fit is it?
It's an interference fit or press fit, however you want to call it.
Yeah. So if I look at my smallest hole and my largest shaft, I definitely have interference, right?
Mhm.
This is 8 thousandths bigger than this. So now I go and take a look at the opposite. If I look at the opposite, now my smallest shaft is 751, but my largest hole is only 750. So I still have interference. So I have interference this way and interference that way. So the fit should be, the type of fit should be interference. So now let's look at this, at the third example. Basic size?
3/8.
3/8, right? Yeah,
Mhm.
0.375. 3/8. Looking at my largest shaft, smallest hole. I've got interference, don't I?
Sure.
7 thousandths bigger. Now I look at my smallest shaft and my largest hole.
That's 3 thousandths difference. So yeah,
2 thousandths difference.
yeah, 2 thousandths, right?
2 thousandths, but the shaft is 2 thousandths smaller than the hole, right?
Right.
So this should be what type of fit? On the one hand, I've got interference. On the other hand, I have clearance. It's like our first example. It's called a transition fit. Right? Because it can be either one, depending on where the limits fall, you know, where the final size falls within the limits. And then the last one, the basic size is 1/4 inch.
Right.
Okay, and now I've got my smallest hole and largest shaft are exactly the same size, and excuse me, my smallest shaft and largest hole show me that I've got clearance. So here I've got line to line because they're the same size, and here I have clearance because the shaft is 8 thousandths smaller than the smallest shaft is 8 thousandths smaller than the largest hole. So that should be I think it's going to call it a line to line, right? Or a line fit, yeah. And it's a line fit is because you've got two limits of the hole, you know, or a limit of the hole and a limit of the shaft that are the same diameter. So it's automatically a line fit, and it could be, you know, depending on where they fall, could be a press fit or a clearance fit, or I should say an interference fit or a clearance fit. You may not have to press it much in order to get it in, but you know, so we don't necessarily call it. I mean, press fit is slang for an interference fit. Let's put it that way. Any questions on that? So the P39, we're, you know, if you guys are working on it and haven't submitted it, this was kind of an ongoing thing because in class over the course of, you know, a number of semesters, some classes have gone through this drawing a lot faster or slower than others. So we kind of kept stringing it along. So it shows up in a number of presentations. Like I said, even though it's got an April 1st due date, which is today, it's not a, I used to extend the due date. I extended the due date all the time because some people had issues with, you know, trying to figure it out. You know, without me giving away the farm to tell them exactly what was going on. You know, I would have to be somewhat cagey about what I would reveal to them. But in the case, you know, the situation we're in now, obviously, I just went ahead and did, you know, most of it online, so that we, you know, we all had an idea, because it's hard to, and especially for those that aren't showing up for this, I just didn't have a, you know, I don't have a good way of communicating what I'm trying to communicate to everybody if they don't show up. So that's why this thing keeps showing up. This could be the last time it shows up. I don't really know for sure. I haven't looked at next week's. I've updated everything for next week, but I haven't really looked at the PowerPoints to refresh myself as to what's in them. So we'll see on Monday. But if you're good, I mean, we're pretty much done with this. Again, you know, this stuff here is kind of moot. You know, I left it in here because I know these PowerPoints might be used by the next person that teaches this class. If it isn't me. If we're still doing this in the fall, who knows? They may be able to talk me into doing this one more time. I kind of like doing it online, to be honest with you, but we'll see what happens. In any event, I leave all this stuff in here just as, you know, reminders for everybody. And, you know, same thing with in the beginning, the what's due and what isn't due. You know, even though it's all different. Otherwise, that's the end of that. Any questions before I minimize this guy?
I'm all good.
You're all good?
I'm good.
All three of you? Okay. One of the, yeah, I'm still here. Let's see, I think I was marching through some of the stuff in this book, in this online book. But I bookmarked this page right here. 7.1 is one of the, that's the assignment for today, this 7174 practice.
Mhm.
It's to do this parts A, D, and F. So there's 3 tables to complete for each part, and it's worth 12 points. And so the page looks like this. So what did I say it was again? A, D, and F, right?
F,
yeah,
right.
A, D, and F. So when you look at A, here's the shaft limits, right? Here's the shaft limits for, and the hole limits for A. Why did it say that? It said 3 tables to complete. For
It's
each
the way
oh, for
the way
each,
I interpreted it was like A would be one table, D would be one table, and F would be another table.
yeah, exactly. That's the way I see it too. So you're doing A, it says, because to, yeah, this would be A, this would be D, and this would be F. So I can't fill in anything on this, but I just kind of wanted to go over that. Yeah, I never noticed that it said that there's 3 tables to complete for each part. I don't think that's correct. I never noticed that before. But that's correct. This would be A, this would be D, and this would be F. Because it doesn't tell you, to, I think when you look at some of the other assignments, that might be correct. Like this, right? See, this is the one, this is 7-2. Now, 7-2, you have to do, there's also 3 parts to this. I forget which 3 they are. But now you're going to say you've got fit 1, fit 2, fit 3, and fit 4. So now you should have actually 12 of these things. 1, 2, 3, 4, 5, 6, 7, 8. There should be another page. I don't know if it shows it, but so that might be one of the pitfalls of the online stuff. Let me take a look at the book. This is page 733.
Well, if it's a copy of the book, it's going to be the same thing.
Oh, you know what it is? I believe the assignment for this one for 7-2 says to only do certain fits for each one. If it says to do, let's say it says A, D, and F, which I'm not sure it's what it is. It might say just do fit 1 and fit 2. So it'd be 1, 2, 1, 2, or fit 1, 2, and 3. So you'd have 1, 2, 3, 1, 2, 3, and 1, 2, and that's still not enough. I don't know. I haven't looked at the assignment, but this is a situation where you got to do more than one. You have to do more than one table for each one of the options, whether it's A, D, and F, or B, C, and G, or whatever the heck it is. I don't remember what assignment that is. So I'm probably confusing the issue, because the other assignment for today is the 7174. Nope, that's not it. 7174 practice and the 77710 preview, and that 77710 preview is just questions.
Right.
So next week, I can confuse everybody next week. Yes. So sorry about that. I probably made it worse than it really was. So for A, D, and F, you're going to fill out A, D, and F. And you're going to, don't forget to circle which type of fit it is. You might have to go back and do some review to figure out what's what. The limits are basically, it tells you what the limits are right here, right? Shaft limits, hole limits. So your limits for A are going to be, for the shaft, are going to be 0.9975 to 0.9963, and your hole limits are going to be 1.002 to 1.000. So, and you write them out whichever way you want. Whether you want to write the hole out the reverse way, 1 to 1.002, I'm okay with that. If you do it the other way, the way the standard tells you, that's fine too, as long as it doesn't confuse you. List the basic size, which is 1 inch, right? What the one, it's the one size, how do I describe it? It's the one nominal size, the even numbered nominal size. So when we talk about nominal size or basic sizes, we're talking about quarter, half, 3/8, 7/16, those types of
Mhm.
nominals. Somewhere buried in here is the nominal size. Like in here, it's 4.75. Here it's 0.50. Here it's 5. You know, here it's 1.25. Here it's 0.125, 2.5, and again here it's going to be 9. So, okay, if we're good, then I think we're done. So I kind of like not having to have us all get kicked out and have to not, you know, then sign back in.
It was rather pleasant. That's true.
Yeah.
Yep.
So there we go. I will see you guys on
Monday.
And have a good weekend.
Okay, Frank, you too.
Yeah, Josh is gone.
Yep.
Yeah, if you have any questions, email me and we'll go from there.
All right.
All right, guys. Take care. Stay safe.
You too.